Learning to Reduce State-Expanded Networks for Multi-Activity Shift Scheduling by Porrmann and Michael Römer.
Welcome to the talk, Learning to Reduce State-Expanded Networks for Multi-Activity Shift Scheduling. My name is Michael Römer. I'm the head of the Decision Analytics Group at Bielefeld University, and this is joint work with my PhD student Till Porrmann. Before getting started, let me briefly review the agenda of this talk. I'll start with introducing the basics of shift scheduling problems and state-expanded network models, and then I'll go into the details of our approach for learning to reduce state-expanded network models. Afterwards, I'll present some first computational results, and then I'll give some conclusions and an outlook. Shift scheduling is a classical personnel scheduling problem that consists in designing a schedule of shifts for a workday covering the demand for a given set of periods, for example, 50-minute periods. Typical objectives in shift scheduling consist in minimizing the number of shifts or employees, minimizing the number of hours worked, and or minimizing the violation of demand constraints. What makes shift scheduling a hard problem is the fact that the composition of shifts needs to respect a couple of rules which may be quite complex. In this example, we only have a couple of simple rules. For example, the total number of work periods per shift, that is the shift length, a break requirement. In this simple example, there's only a single break, but in general there may be multiple breaks with different length, and there's often also a restriction on the length of certain work blocks. For example, there may be a minimum length of 2 work periods here and a maximum length of 5 work periods for each block of consecutive periods of work. In this talk, we focus on so-called multi-activity shift scheduling problems. In this kind of problems, there are different types of demand, that is different types of activities which need to be covered. These activities have their own sets of rules. For example, there may be a minimum and a maximum number of consecutive periods per activity, and the composition of work blocks from activities may also be constrained. When it comes to solving multi-activity shift scheduling problems using mathematical programming, there are a couple of formulations that you can find in the literature. Probably the most famous one is the set covering formulation, which is proposed already by Danzig. Then there are some so-called implicit models, which have been recently shown to work not only for mono activity but also for multi-activity shift scheduling problems in a paper by Dahmen. And then there are also some approaches using formal languages, namely context-free grammars, which can be used in MIP formulations or formulations based on finite state automata. On this slide, you find an example for such a state-expanded network, which can be used for encoding the simplified shift scheduling problem presented on one of the first slides. The central property of this network is that the set of paths in this network from the source to the sink node is equivalent to the set of feasible shifts. That means that every feasible path, every feasible shift is represented in the network, and at the same time every path represented in the network can be mapped to a feasible shift. In order to establish this key property, nodes are associated with rule-relevant state information in a way that only feasible states are included in the graph, and arcs are associated with transitions which are induced by work or break assignment. In order to model this simple shift scheduling example, we use the following state attributes. The period index P, depicted here on the x-axis, the number of periods worked, which is depicted here on the y-axis, and the number of breaks taken so far, and the type of the previous assignment, which are visualized using different types of nodes. Let us now see how a given shift is represented as a path in this network. Let's take the shift 0 from the one of the previous slides here. The shift 0 starts with a 2-period work block, and as noted before, there's only a single arc which represents the lower bound of 2 periods for this work block. This work block arc is followed by a break arc here, which is then followed by 3 work block arcs, namely one 2-period work block arc and then 2 additional arcs representing additional days in the work block. Then this arc goes to the sink and back to a circulation arc to the source. What is interesting here and what is important here is that we, in case of an anonymous problem, we only need a single state expanded network for the whole problem. This means that if we want to represent a second shift here, this second shift can form a second path, source sink path in the network. And as we will see later, this can be modeled as a 2-unit flow in a state expanded network, which is then embedded in a mid model. So this is the mixed integer linear programming formulation based on state expanded networks. And as you may observe here, the flow variable x in the network is an integer variable. It's not a binary variable, since the number of flow units through this network corresponds to the number of shift which will be constructed. And so this central part of this model are the flow balance constraint. And due to the fact that all shift composition rules are embedded in the network, we do not need to explicitly model any shift composition rules in the mathematical model. The only rule that we need to consider here are the demand covering constraints, which then enter, for example, here as using a penalty term, the objective function. State expanded network formulations, such as the one depicted on the previous slide, have 2 key properties. On the one hand, they give rise to very strong formulations with a very small LP-IP gap. However, the model instances tend to become very large for large-scale problem instances, which may, of course, lead to large computation times. A possible solution to this issue is to heuristically reduce the network by removing unpromising nodes or arcs. Typically, this is done using simple reduction heuristics, for example, in this case, based on the number of periods work. But these reduction heuristics often fail to find a good balance between solution time and solution quality. This brings us to the key idea of this paper, namely using machine learning for guiding the reduction of state expanded networks. As recently reviewed by Benjo, Lodi, and Provost, there are various approaches for combining machine learning and combinatorial optimization. First of all, there's end-to-end machine learning for combinatorial optimization problems. Then machine learning may be used for offline configuration of combinatorial optimization. It may also be used for guiding online decision-making within combinatorial optimization algorithms. One can even embed machine learning models into combinatorial optimization or use machine learning for learning model components such as constraints of combinatorial optimization. The approach presented in this paper is somewhat different. Our goal is to use machine learning to obtain a high quality and efficiently solvable primal approximation of a combinatorial optimization model. More particular, the key idea is to use machine learning for reducing state expanded networks. How do we do this? We use node and instance attributes to predict which parts of the state expanded network may be useful for finding the optimal solution, and the rest is simply removed. We can train this model using a set of near optimal solutions from different instances. Why do we think that this idea is promising? We think it is promising because machine learning is not used to predict particular solution, but only to predict promising parts of the solution space. This leads to the insight that combinatorial optimization can still play out its major strength, namely searching a combinatorial solution space. Let's go into our approach in some more detail. The key components of our approach are predicting the flow through nodes and removing unpromising nodes and arcs. The flow prediction is based on state attributes of the nodes and on instance information such as workload per employee. For machine learning, we use the XGBoost regressor, and for training data, we use flow variable values from near optimal solutions. An important observation here is that an overestimation of a flow is not a big deal, since in the optimal solution only a fraction of the nodes and arcs is used anyway. An important factor for the efficiency of our approach is that we do not predict the flow through activity-specific nodes, but that we aggregate the flow through these activity-specific nodes into a single node. Why do we do this? Because this, first of all, this avoids symmetry issues, which are inherent in the formulation in case of multiple activities. And second, it increases generalizability because the machine learning model now becomes agnostic for the number of activities. That means that we can use, for example, a 5-activity instance to train a model that is later used for 10-activity instances without any problem. The last step, that is removing nodes and arcs based on the predicted flow, works as follows. First of all, we define a threshold. And whenever the predicted flow falls below this threshold, a node is marked for removal. Since it may happen that some unmarked nodes are no longer reachable because all its predecessors are marked for removal, we ensure reachability by recursively unmarking its predecessors. Finally, we remove all marked nodes and their adjacent arcs. Let us now review some first computational results with our approach. For these results, we used the instances from Demarçay et al. 2005. This is a set of multi-activity shift scheduling problems instances, which have been used in several previous papers. It consists of 100 instances and 10 instances per each number of activities from 1 to 10. To solve these instances, we used a standard notebook computer in Gurobi 9.1, and for the exact problem reported in this part of the table, we allowed a time limit of 60 minutes. For the full model without any reduction, we were able to solve many instances to optimality, but for the largest instances, the approach began to struggle to solve the instances to optimality within the 60 minutes time limits. The instances are not too large, but large. They have more than 200,000 columns and more than 77,000 rows, and the number of nodes in the network amount to 76,000. As mentioned before, one approach for trying to get good solutions quickly is to heuristically reduce the size of the state-expanded network. The second column of this table shows the result from applying a simple heuristic network reduction rule that removes all nodes representing long shifts with long hours of work. The results show that while the reduction with this rule is only moderate, the solution quality still is not very good. In particular, only less than half of the instances we were able to actually find the optimal solution. Fortunately, the results get much better when we use the machine learning based reduction proposed in this paper. In this case, in 9 out of 10 cases, we found the optimal solution despite the fact that the network size was substantially reduced by more than 60% on average. With respect to the computation time, the average solution time was 100 seconds, and even for the largest instances with 10 activities, the average solution time was only 324 seconds, that is slightly more than 5 minutes. So how did we come up with the results presented on this slide? First of all, it's important to note that we used a 3-fold partitioning of the 100 instances, where each fold contained the instances with different activity numbers. In any case, 2 folds were used for training and 1 for evaluation. This results in the fact that every instance is solved using the machine learning model which was trained without the instance itself. The reduction thresholds were created or were devised empirically. We used two different thresholds for the different sizes of the instances, and we gave a time limit of 10 minutes. Finally, the last two columns of this table show that our approach is similar in performance to the state-of-the-art Lagrangian matheuristic presented by Hernandez Leandro and others in 2019. So let me briefly conclude this talk and give a short outlook. First of all, I think the preliminary results presented here showed that the approach generally works. Our approach was competitive with state-of-the-art heuristics, and even in the majority of the cases we were able to obtain the optimal solutions for the instances under consideration. Why do we think that this idea represented in this talk is promising in general? We think that it is promising because machine learning is not used to predict particular solutions, but predict promising parts of the solution space, which allows combinatorial optimization to still play out its strength, namely searching a combinatorial solution space. Our next steps are applying the approach to additional problem classes, using additional information, such as information from the LP relaxation, and using a reinforcement learning style approach to avoid the need for providing optimal solutions in advance. Thank you for your attention, and we are looking forward to your questions.
All right, thank you. Thank you, Michael. Is there any questions? Roland, I see your hands up, but I think that might be a hand from the last time around. But if it's not, you can go ahead. Oh, there's one from Vienna. Go ahead, Vienna.
Yes, thank you for your talk. So just, I have two questions. The first one is about the breaks. So you can also have multiple breaks. So in which, I mean, what is the maximum number of breaks in which your approach would work? The second question is, I think you had just 100 instances. So, I mean, it's interesting that the machine learning approach was working pretty well with this number of instances. Can you comment on that?
Okay, first question was regarding the number of breaks. So these particular instances allow two numbers, up to 3 breaks, 2 short and 1 long break. I don't think it's very, so the number of breaks definitely have an impact of the size of the state space, which then has an effect on the number of nodes in this state expanded network. So this is, it will work anyway. And your question regarding the generalization within the set of 100 instances, you should observe that we don't, our training set does not consist of 100 instances, but 200,000, 70,000 nodes per instance, because we have 7, for each solution of the instance, we have these number of variable values, so which we can use for training. As I also mentioned before, is that we, by using this, let's say, aggregation trick, we are able to generalize even beyond instances of the same number of activities.
Okay, thank you. Yeah.
So there's a question from Sasha in the chat asking, might there be some merit in applying the core idea to an iterative setting where you could have a small graph and then iteratively add new nodes to the graph as you look at the solutions as it goes?
I think that is exactly what last point on my slide was pointing to, namely this is one of our next steps, because I think the approach will generalize. So you can start with a highly reduced network and use the state information of the optimal part in this reduced network for learning. And then I'm pretty sure that our approach will, the next network using this trained networks will provide better solutions. So this is actually one of the next steps that we want to tackle.
Okay, thank you. Last question to Louis Martin.
Hi, great talk, Michael. I was wondering, did you use well, you didn't mention it, but did you use any features from the actual demand curves? There is one thing in this in these instances, if I remember how we built them in the early 2000s, is that we took like real demand curves from about 100 stores, and then we kind of randomly assigned them or not accumulated them to create the instances. So it's possible that the same demand curve appears in numerous instances for different activities or something like that. So I would look into it to see the correlation with the actual demand curve, and maybe that could be a lead to having features in the machine learning model that actually extract the demand curves to figure out when a shift would be useful or not in a given instance.
Yeah, so we do this in, first of all, in an implicit way, because as an important instance feature, we use the work density. That is the relation of the amount of total working hours to the number of employees in the instance. So this is one feature which takes this into account somewhat. And then, admittedly, these instances are very structured in a certain way that even the period index. So there are some periods there's no demand at all, and there are some periods. So the period index gives some information about this 0-1 thing, but of course this was one idea of taking the demand in a certain period or in a time window of periods into account, but at least in this part, we did not really need it. It did not contribute too much of the.
All right, thank you, Michael, for that nice talk, and Till as well for nice work.